integrals. Our final section for today is Curtate future lifetime, Kx and Ex. In many insurance applications, we are interested not only in the future lifetime of an individual, but also in what is known as the individual's Curtate future lifetime. The Curtate future lifetime random variable is defined as the integer part of future lifetime and is denoted by kx for life-aged x. We can think of the Curtate future lifetime as the number of whole years lived in the future by an individual. As an illustration of the importance of Curtate future lifetime, we consider the situation where a life-aged x at time 0 is entitled to payments of 1 at times 1, 2, 3 and so on, provided that x is alive at these times. Then the number of payments made equals the number of complete years lived after time 0 by x. So this is the Curtate future lifetime. We can find the probability function of kx, and this is the value of this probability function. The expected value of kx is denoted by ex. This is our expected value. So ex equals to expected value of kx and is referred to as the Curtate expectation of life, even though it represents the expected Curtate lifetime. So our ekx equals to sum of px, and the lower limit for summation is k equals to 1, so pay attention to this. Similarly, we can derive the formula for the squared kx, and this will be this double sum of k times kpx minus ex. As with the complete expectation of life, there are few lifetime distributions that allow our expected value of kx and expected value of k squared x to be calculated analytically. For more realistic models such as Gompertz, we can calculate the values easily using R. Although in principle we have to evaluate an infinite sum, at some age the survival probability will be sufficiently small, and we can treat it as an effective limiting age. As the Curtate future lifetime is the integer part of future lifetime, it is natural to ask if there is a simple relationship between ex and ex without the dot on top. We can obtain an approximate relationship by writing this formula. This is our approximate relationship. If we approximate each integral using the trapezium rule for numerical integration, and I'll provide the appendix for you, we will obtain this kind of formula. And the most important result is we have an approximation that is frequently applied in practice. So our ex equals to ex plus 0.5. So in our next lectures we will meet a refined version of this approximation. Although laws of mortality such as Gompertz law are appealing due to their simplicity, they rarely represent mortality over the whole span of human ages. A simple extension of Gompertz law is Makeham's law. So this is the formula for the Makeham's law. I'll just write the name, Makeham's. This is very similar to Gompertz law, but adds a fixed term that is not age-related. So this is it, A. That allows better for accidental deaths. The extra term tends to improve the fit of the model to mortality data at younger ages. In recent times, the Gompertz-McCaham approach has been generalized further to give the GM formula, the Gompertz-McCaham formula. And here in this formula we have H1 and H2. These are the polynomials in x of degree r and s respectively. Today we noted the importance of the force of mortality. A further significant point is that when mortality data are analyzed, the force of mortality is a natural quantity to estimate, whereas the lifetime distribution is not. The analysis of mortality data is a huge topic and is beyond the scope of our lectures. An excellent summary article on this topic is McDonald, 1996. I'll provide you the link. The quantity f0x over s0x, which actually is called the force of mortality at age x, is known as the hazard rate in survival analysis, and in reliability theory it is called the failure rate. So that's it for today.